Score matching has become this absolute cornerstone of modern machine learning, right? I mean, it's the engine behind energy-based models and, maybe more importantly, the diffusion processes that are powering so much of the generative AI we see today. But, it has this well-known Achilles heel. It's built on the fundamental assumption that you have complete data. And let's be honest, in the real world, whether you're looking at medical records or financial data, that's a luxury we almost never have.
Exactly. So today, we're going to dive into a paper that really tackles this problem head-on. First, we'll get to the heart of what we're calling score matching's missing piece. Then we'll explore the paper's two very clever paths to a solution. We'll see how they held up in a pretty tough experimental gauntlet, analyze their performance under pressure, and finally, we'll look at what this all means for the field moving forward. Okay, let's get right into it. The fundamental goal of traditional score matching, as we know, is to minimize something called the Fisher divergence. You're basically training a model, and you want its score function to perfectly mirror the score of the true data distribution. Right, and the real power of the score function is that it lets us model these incredibly complex distributions without getting tangled up in those often intractable normalizing constants. But here's the catch. The moment even a single coordinate in your data is missing, the whole elegant framework just breaks. You literally can't evaluate that full score anymore.
And this is where the paper makes its first really clever move. Instead of trying to fill in or impute the missing data, the authors just adapt the objective itself. The new goal is to match the marginal scores of only the data we can actually see. It's a really smart workaround, but it creates a new headache. Calculating this new marginal score requires integrating over all those missing dimensions, which, you guessed it, is intractable for most non-trivial models.
And that very intractability brings us right to the paper's core contribution. To solve this new problem they've set up, the authors propose two distinct, but as we're about to see, really complementary methods for estimating these tricky marginal scores. Okay, so the first method is importance weighting score matching. It's the most direct approach. You can think of it as a clever application of a classic technique. You use a proposal distribution to kind of guess what the missing values are, and then you apply these importance weights to correct for any difference between your proposal and the true conditional distribution. It's conceptually pretty straightforward, but the quality of that proposal distribution can really make or break its performance.
The second method is a more sophisticated variational approach. The authors call it a gradient-first method. The key idea here is, instead of estimating that difficult integral and then taking its gradient, they just switch the order. This reformulates the problem into one of estimating conditional expectations, and then they train a separate helper neural network to approximate those. It's a move that cleverly sidesteps the potential bias you can get with the importance weighting method, and it turns out to be much more stable as the data gets more complex.
So you can really think of these as a complementary toolkit. You've got the importance weighting method, which is simpler and works great in lower dimensional settings, or when you just don't have a lot of data. And then you have the variational method. It's more complex to implement, sure, but it is engineered to handle the chaos of high-dimensional data where that IW approach might start to struggle. So now for the real test, right? To see if these approaches actually work, the authors pitted them against two key baselines. The first is a pre-existing EM-like method, which is known to have some bias issues. And the second is a naive, zeroed baseline that, as the name suggests, just fills in all the missing values with zero.
Their first set of tests were on simulated data where the ground truth was known, which means they could measure the error precisely. They started with a 10-dimensional truncated Gaussian to test a pretty constrained setting, and then they used a much more complex, ICA-inspired non-Gaussian model, where they could actually vary the dimensionality to really stress test how well these things scale. Next, they moved on to a really practical downstream task, estimating Gaussian graphical models. Now, this is a genuinely difficult problem, learning the dependency structures in data. They used both simulated graphs and two really challenging high-dimensional real-world datasets, S&P 100 stock data and yeast gene expression data. So the big question is, how did these new methods actually perform when they were put through this gauntlet?
All right, so let's look at figure 1. This shows the results for that 10-dimensional Gaussian model. The y-axis is Fisher divergence, so lower is better. The proposed importance weighting method, that's MARG-IW in blue, you can see it achieves the best performance. The existing EM approach is pretty close behind. But wow, the real story is that red line. The naive, zeroed method completely fails to converge. It really highlights just how inadequate simple imputation is. Now things get very interesting when we crank up the complexity. This is the non-Gaussian model from Figure 2, and you can see on the x-axis the dimensionality is increasing from 10 all the way to 50. The variational method, margvar in green, is now the unambiguous winner. And just look at how its performance gap over the other methods widens as the dimension grows. This is really powerful empirical confirmation of the theory. The variational approach is built to scale. And that trend is even more pronounced when we get to the real-world data. This is Figure 6, showing the S&P 100 stock data experiment. Here, the metric is area under the curve for detecting dependencies, so higher is better. The x-axis is the probability of an entry being missing, from 10% up to 50%. The result here is just striking. The green line, our variational approach, consistently and decisively outperforms every other method at every single level of missingness. And we see the exact same story in Figure 7 with the yeast gene data. It's another high-dimensional, really complex dataset, and once again, that green line representing the variational method is just sitting comfortably above all the others. This really solidifies its position as the more robust and reliable solution for these challenging real-world applications. So what's the big takeaway here? This paper doesn't just present a single solution. It really delivers two effective and complementary methods. It gives us a theoretically grounded framework that finally adapts the power of score matching to the practical reality of incomplete data. And that's a significant and long-standing gap in the field. And the authors are also very clear about the path forward. There is a bit of a theoretical gap to bridge in formally connecting the error on the marginal score back to the error on the full data score. But what's most exciting, I think, is that because this entire framework is compatible with denoising score matching, it can be extended to diffusion models. That just opens the door for much more robust, generative modeling and data imputation on all kinds of incomplete datasets. At the end of the day, this work pushes us closer to answering a really fundamental question. How do we build systems that learn from the world as it actually is? Imperfect, incomplete, and messy. Exactly. It equips the field with a powerful new set of tools for finding the signal within the unavoidable noise of real-world data.